I guess we're here. So, hello. What I'm hoping is that by the time you watch this video, you will have this information done. You will have eaten a Tootsie Pop and recorded some data, and then you will have in class figured out the change in radius and how the change in radius divided by the change in time is for each of your things. And then you would have found the mean of all the numbers in this column. If you haven't done that yet, then, well, stop. Okay, come back later at some other point. So you'll have had a bunch of data. And you also should have had data from everybody in the class. So this little table here and the notes all filled out with everybody's information. And then what we ultimately will do, or should have done already, was to come up with a class mean. So we have taken the average of all the averages and come up with some number. And I'm just going to, for the sake of moving forward here, I'm going to pretend that number is about 0.02, in this case, millimeters per second. And it'll be a negative value. So whatever number we actually came up with as a class, and when we did this ourselves, you're going to want to use that number as we move forward, okay? And we said that that was what we're going to call the change in radius over the change in time, drdt, change in radius, because we were spreading this out over quite a few calculations, so we're going to be comfortable enough saying that drdt is, in this case, negative 0.02 millimeters per second. Your numbers may vary, actual mileage may vary as well. So the question that we're ultimately trying to answer about this, with this data that you've collected about the Tootsie Pops, is how fast is the volume of the Tootsie Pop changing when the radius is, and we'll just pick a number. In this case, I'm going to say when the radius is 12 millimeters. That's a little more than millimeters, a little more than a centimeter. So it's a fairly small Tootsie Pop. So what we're gonna make some assumptions here. We're gonna assume that this Tootsie Pop is spherical, and so thus the volume of our said spherical Tootsie Pop is going to be 4/3 pi r cubed. We know that the radius is changing at a rate of, and I'm just using this number again. I'll say it again because it's just a number that I sort of made up, and it's probably pretty close to the number you came up with, of drdt equals negative 0.02 millimeters per second. We want to know how is the volume changing with respect to time, dv dt. Okay? We know dr dt. Okay? If you do some little backwards math, what we can do is we could multiply dr dt by dv dr, and if you notice, like, kind of in a bizarre way, the dr's cancel out, and so we'd be left with dv dt. We know what dr dt is right there. We have an expression for volume that's dependent on the radius. So what we're going to do is we're going to first find out what dv dr is, and that's just going to be the derivative of this volume equation with respect to the radius. So it's all nice in a power rule sort of situation. We've got a big constant out in the front. We can bring 3 to the front of the thing. 3 times 4/3 is 12/3. 12/3 is the same as 4. So we have 4 pi r squared. That's what dv dr is. Okay? So in our little equation here that dv dt is equal to dv dr times dr dt, we know what dv dr is. So we can just plug away in 4 pi r squared. That's dv dr. dr dt is negative 0.02. And ultimately we want to know how's the volume changing when the radius is 12 millimeters. Okay, and again, so we just plug 12 in at this point. 4 times pi times 12 squared times negative 0.02. Okay, and that turns out to be, I'm sure, some number. If I had a calculator handy, which I do, I will just calculate it, and then I'll just cut this portion out. Since you watching me, 4 times 3 times 12 times 0.02 negative 36.1728. Okay, and here in calculus class, negative 36.172, okay, 8 actually. And we always do everything, we either round or truncate, so in this case we could make the answer negative 36.172, that would be truncated, or negative 36.173, that would be rounded. Truncate means just cut the end off. Round means just what round means, and either way is an acceptable answer. 3 decimal places, rounded or truncate, that's the rule. So in this case it's 36.1728 cubic millimeters per second. So every second that you were sucking on the Tootsie Pop as a class, we were able to remove 36 cubic millimeters of Tootsie Pop sort of material, at least at this particular time when the radius was 12 millimeters. When the radius was bigger, we would get a larger number. When the radius is smaller, you get a smaller number because it's just about the surface area of the Tootsie Pop. So why this is called related rates, and I don't know if I've used that word before, but the rate of change of volume is related to the rate of change of radius. Okay, and so thus related rates because the two rates are related. Okay, so related rates. That's the thing. Talk about that little problem a little bit later. So a pebble is dropped into a pond. This is another related rates problem. Pebble is dropped into a pond, forming concentric ripples whose radii increase at a rate of 1 feet per second. Speaking soothingly, because it's a soothing image. When the radius is 4 feet, how fast is the area of the ring changing? Alright, what we want to know is we want to know how fast the area is changing. So what we want to know is the rate of change of area with respect to time. Okay? We know that the radii is increasing at a rate of 1 feet per second. So the rate of change of radius with respect to time is 1, in this case, foot per second. Okay? What else do we know? We know that these rings are like circles, okay, with radius r. And we know how to find the area of a circle, right? Area of a circle is pi r squared. So like we did on the last problem, we're going to try to use somehow the fact that we know how the radius is changing to figure out how the area is changing. And those two rates are related to each other. And so the bridge that we're missing is dA dr, how the area is changing with respect to radius. So in order to figure out what dA dr is, we take the derivative of this area with respect to the radius. So dA dr, that means with respect to means that's the variable that we're differentiating. Okay, we're differentiating r with respect to a. 2 is going to come down in front, pi r. Clap your hands once if that looks familiar. That looks like a familiar formula that you've seen. Okay, good. So dA dr is 2 pi r. So we can just go ahead, plug dA dt is equal to 2 pi r times, in this case, 1 dr dt. We want to know how fast when the radius is 4 feet per second. So when r equals 4, again, this little bar line means evaluate when. So 2 pi times 4 times a 1, I think that's 8 pi. So 8 pi feet squared per second. Yes, and that's how the area is changing with respect to time. Well, a couple of related rates problems. Again, these two rates are related to each other. How this changes, if this was changing faster, then this would change faster. Okay, so related rates. What I want you to do with your version of the Tootsie Roll Pop after you've got the calculations is just to give me a little write-up about the process. So actually do out that problem. So do the problem out. We have the data already. You're going to do the math, and just, what do you learn from? What do you learn from doing this little related rates thing? What does it tell you about the Tootsie Pop experiment? What sort of error might we have in it? It doesn't need to be any formal sort of thing, doesn't need to be typed up, but just sort of a conclusion and observations based on it, and that'll be a handed-in sort of a situation when you get to that place and things. Okay, and then those are the problems, but you already knew that already. So, related rates. You can do it. Thanks for watching. If you learned something, talk to you soon.